The terrifying places in space where death begins before you arrive. Distance is the oldest form of shelter you know, not as a theory, as something your body learned before your brain had words for it. Pull back from the edge. Step away from the heat. Put space between yourself and the thing that can hurt you. The animal logic is sound. Distance means time. Time means survival. It works on Earth. It has always worked on Earth. But the universe was not built around this logic. There are places in space, not hypothetical, not edge cases, not science fiction, where the instrument of death travels outward faster than any warning can, where the radius of lethality extends across distances so large that entire star systems, entire galactic neighborhoods fall inside them without knowing, where the object responsible may be so far away that the light from the event that generated the danger takes longer to arrive than human civilization has existed. Not metaphorically. Not as a poetic way of saying that space is unfriendly. Specifically, there are known objects with coordinates, studied by named instruments operated by living scientists, whose kill radii extend for thousands of light years in certain directions, and Earth has been inside the kill radius of at least one such event. The evidence is fossilized in the rock beneath your feet. The species that were lost are the gap in the record, the absence that tells the story. You survived that event. Or rather, the life that eventually became you survived it, narrowly, in the right ocean trench, in the right hemisphere, at the right depth. The event came anyway. It did not wait. It did not negotiate. What follows is a careful description of those places. What they are, where they are, how their reach extends before them like a long shadow. And, at the end of this, something that might not be comforting in the conventional sense, but that is true, and that is, in its own way, remarkable. If this is the kind of night you return to, subscribe. It helps this quiet universe keep growing. Let's begin. December 27th, 2004. 18 years before the James Webb Space Telescope sent back its first images. 4 months after Cassini-Huygens completed its first Titan flyby. A quiet Tuesday in terms of space news. At 21:30 UTC, the Earth's night-side ionosphere lit up. Not from within, from outside. From 50,000 light-years away. A distance so large that if you drove at highway speed and never stopped, you would die. Your grandchildren would die, and perhaps 100 generations more would live and die before you covered a fraction of it. From that distance, a flash of gamma rays arrived and hit the atmosphere with enough energy to measurably deform the ionosphere on the side of Earth facing the event. Satellites detected it. Radio operators at low frequencies briefly lost contact as the ionosphere thickened under the bombardment. The signal lasted approximately a fifth of a second. In that fifth of a second, the object that generated it, a magnetar called SGR 180620, had released more energy than the sun emits across 250,000 years. Complete years. Not a day less. Here's what that number doesn't communicate. The event was already over. The flash had been released, traveled for 50,000 years, crossed that incomprehensible distance, struck a planet it had no awareness of, and dissipated, and the object had moved on. SGR 180620 was quiet by the time the light landed. The announcement arrived before the emergency did, not in the other direction. The danger had already resolved itself while traveling. Now, SGR 180620 is 50,000 light-years away. That flash, at that distance, was strong enough to affect Earth measurably. Not to damage it significantly, but to touch it. The question that keeps coming back is a simple one. How much closer would it need to be to end everything? The answer has been calculated. Astronomers and astrophysicists have produced estimates, not guesses, but calculations derived from the physics of how gamma and X-ray radiation interacts with Earth's atmosphere and the biological systems it protects. A magnetar burst of the scale SGR 180620, produced in 2004, if it originated from within roughly 30 light-years of Earth, would likely produce enough gamma-ray flux to strip the ozone layer over the facing hemisphere in a matter of hours. The depletion would be significant enough to allow ultraviolet radiation to reach the surface at levels that would damage DNA in exposed organisms. Not immediately, but over months and years as the ozone layers slowly recovered. For a gamma-ray burst, a different and far more energetic event, the lethal radius in the beam direction is calculated at roughly 6,500 light-years. Not 6 light-years, not 60, 6,500. The Milky Way disk is about 100,000 light-years across. A single GRB aimed correctly could sterilize a cylinder of galactic space 6,500 light-years long and tens of light-years wide. Thousands of star systems in a single event. The Milky Way produces approximately 1 or 2 gamma-ray bursts per million years. There are an estimated 400 billion stars in this galaxy. The geometry is not in anyone's favor across long timescales. These are not speculative numbers. The ozone depletion from ionizing radiation has been modeled in peer-reviewed papers. The kill radius is a number you can look up. It is large enough that living at what we instinctively think of as a safe distance from a violent cosmic event means essentially nothing. The danger travels at the speed of light. Safety would require knowing in advance that you are outside the cone. We don't know that yet. Most stars, when they die, leave something behind. A star like the Sun, at the end of its life, will swell into a red giant, shed its outer layers in a planetary nebula, and leave a white dwarf, a compact remnant the size of Earth, but with the mass of the Sun still packed inside it. Hot, dense, slowly cooling over billions of years. Heavier stars, born with 8 or more times the mass of the Sun, die differently. The core collapses faster than the physics can accommodate. Protons and electrons are forced together, producing neutrons. The core, that's all that remains, is a ball of neutrons roughly 12 miles across, with the mass of 2 suns packed inside it. A neutron star. A magnetar is a neutron star with an anomalous magnetic field. A field so strong that the numbers used to describe it become essentially meaningless as language. The magnetosphere of Earth, which shields life on this planet, measures roughly 50 microteslas at the surface. A standard neutron star's field measures around 100 billion Tesla. A magnetar reaches 10,000 trillion Tesla. If there were a magnetar where the moon currently sits, the force of its magnetic field would tear the iron in your blood out of your veins before you've finished reading this sentence. And the field isn't static. Magnetars experience starquakes, moments when their rigid crystalline crust fractures under magnetic stress, releasing enormous amounts of energy in fractions of a second. The 2004 event from SGR 1806-20 was one such starquake. The crust cracked. Energy released. The light left. 50,000 years passed. It arrived on a Tuesday and briefly disrupted the ionosphere of a planet whose largest concern that month was news cycles. But here's what almost nobody considers when they first encounter this. The radius of a magnetar's magnetic field extends outward long before its visible light. You would enter the killing zone of a magnetar before the magnetar would be anything more than a dim point of light to your instruments. Death, in this case, begins before you see the source. Imagine the approach, not a catastrophic arrival, a gradual one. At 100,000 kilometers from SGR 1806-20, you are well inside the moon's orbit in terms of relative distance. The magnetar ahead of you is a point of light, dim in optical wavelengths, brighter in X-ray. Your instruments are reading elevated radiation levels. The magnetic field at this distance is already more powerful than anything on Earth's surface, but your shielding holds. You are not yet in danger from the field gradient itself. At 10,000 kilometers, the situation changes. The field gradient, not the field itself, but the rate at which it changes over distance, is strong enough to exert different forces on different parts of your body. The iron in the hemoglobin in your head and the blood in your feet is experiencing different magnetic conditions. The effect is subtle but measurable. The instruments are screaming. At 1,000 kilometers, you die. Not from heat, not from being struck by anything. The magnetic field at this distance is approximately 10 million times more powerful than Earth's. The quantum states of electrons in the atoms of your body are forced into alignment with the field. The chemistry of your cells stops being chemistry and becomes something else. The bonds that hold organic molecules together are disrupted at the quantum level. It happens in milliseconds. You never see the surface. You die in what we would describe as empty space, with the magnetar still a tiny bright point ahead of you, roughly 3 times closer than the moon is to Earth. For context, the moon is approximately 384,000 kilometers away. You die at 1,000. The danger doesn't wait for proximity. The field extends outward into the emptiness between you and the source, and you enter it without announcement. And this is one of the calmer kill mechanisms in the universe. The actual sequence of the 2004 Magnetar event is worth holding for a moment. December 27th, 2130 UTC. The gamma-ray satellite R-HESI, a NASA craft studying the sun, recorded a burst so intense it overloaded its detectors. Not dimmed them, not surpassed their range. Overloaded them. The detector saturated and could not record the actual peak. Instruments designed to study the most energetic events on the sun couldn't measure the peak of something 50,000 light-years away. Simultaneously, the satellites Swift, RXTE, Integral, and Messenger all detected the same event. The Messenger spacecraft was en route to Mercury. It detected the burst through its solar panels. The night-side ionosphere of Earth, the part of the atmosphere usually quiet because it isn't being struck by solar radiation, lit up with gamma-ray-induced ionization. Radio operators at very low frequencies noticed the anomaly. The entire event lasted less than a second. If SGR 180620 were the same distance from Earth as the Crab Nebula, roughly 6,500 light-years away instead of 50,000, the 2004 event would have been powerful enough to match the estimate for a GRB-class ozone depletion event over the hemisphere facing it. There would have been no warning. The first signal and the damaging radiation would have been the same signal. At the moon's distance, there is essentially no calculation. There is only the millisecond between now and after. The object that did this has done it before. It will do it again. It is doing it right now. Not the 2004 burst specifically, but magnetar activity is ongoing. The question is always the same. Where is the burst directed? And the direction is random. SGR 1806-20's field axis doesn't know Earth exists. The next starquake won't pause to calculate angles. We have mapped it. We have named it. We have published papers about it. It doesn't care. A gamma-ray burst is the most energetic event in the universe after the Big Bang itself. They come in two kinds. The short ones, under 2 seconds, are believed to come from neutron-star mergers, two dead stellar remnants colliding and releasing the energy of their combined masses in a jet of radiation. The long ones, over 2 seconds, often lasting minutes, come from the collapse of massive stars, the same events that produce supernovae, but in cases where the collapse generates a relativistic jet. Both types produce a beam, not an omnidirectional flash, a collimated jet of gamma-ray radiation that extends outward from the source, narrower than you might expect, roughly a few degrees of opening angle in most cases, but with an energy density inside the beam so extreme that it can be detected across billions of light-years. We have detected GRBs from distances greater than 12 billion light-years. Events that happened when the universe was less than 2 billion years old, still arriving. The beam travels at the speed of light. It does not slow down. It does not disperse significantly over intragalactic distances. What hits you at 6,000 light-years is functionally identical to what left the source, just less concentrated. But less concentrated from incomprehensible to merely lethal is not a meaningful improvement. The photons arrive first. Then comes the consideration that what you just received is only the leading edge. Here's what changes the frame entirely. There are an estimated 44 Wolf-Rayet stars within roughly 8,000 light-years of Earth. Wolf-Rayet stars are massive, unstable, rapidly losing mass to extreme stellar winds. Several of them are potential GRB progenitors. Some of them are within the 6,500 light-year lethal radius. One of them, in particular, is worth discussing separately. At 8,000 light-years from Earth, in the direction of the constellation Sagittarius, there is a binary star system that astronomers have watched with some care for decades. It's called WR104. One of the stars in this system is a Wolf-Rayet star, a dying massive star that has shed most of its outer hydrogen layers and is burning heavier elements at an unsustainable rate. The visual appearance of the system is remarkable. The stellar wind from the Wolf-Rayet star spiraling against the companion produces a pinwheel nebula, a structure that rotates roughly every 8 months and is one of the most visually striking objects ever resolved in the infrared. The geometry of that pinwheel tells you something uncomfortable. The pinwheel appears nearly circular in our observations. Not elliptical, not stretched, round. When a spiral structure appears round, it usually means you are looking down its axis. When you look down the axis of WR104's spiral, you are looking down the axis of the Wolf-Rayet star. You are looking down the barrel. If WR104 undergoes core collapse and produces a gamma-ray burst, and it is a plausible candidate for exactly that event, the jet would point toward Earth. Not precisely. Astronomers estimate the alignment is within roughly 16 degrees. Whether 16 degrees is inside or outside the beam width of the specific event depends on variables we cannot know in advance. WR104 has not yet collapsed. It will at some point. In the next 100,000 years, perhaps. Perhaps sooner. The physics doesn't provide a date. If it happens and the beam catches Earth, there will be no warning. Gamma rays travel at the speed of light. The only precursor would be a faint brightening in optical wavelengths, a supernova, arriving simultaneously with or slightly before the burst. There is no meaningful interval between warning and impact. 8,000 light-years is well inside the kill radius. 445 million years ago, something ended approximately 85% of all species on Earth. The Ordovician Silurian extinction is the second largest mass extinction in Earth's history. Life was almost entirely marine at that point, and the fossil record for this period shows a boundary that is difficult to explain cleanly. On one side, a thriving, diverse ecosystem of trilobites, brachiopods, cephalopods, graptolites. On the other side, roughly a third of all genera dawn. The conventional explanation is a glaciation event, a sudden and severe cooling of the planet, probably triggered by the uplift of the Appalachians, drawing down carbon dioxide. This is well documented and widely accepted. But there is another hypothesis that fits data the glaciation alone doesn't fully explain. The pattern of species loss in the Ordovician shows a geographic signal. The extinctions are not evenly distributed. Species in shallow, high-latitude water, the kind exposed to the sky, show disproportionately higher loss than species in deep water or equatorial regions shielded by a thicker column of water. This is consistent with what you would expect from a hemisphere of ozone depletion allowing ultraviolet radiation through. The hypothesis, a nearby gamma-ray burst, nearby meaning within 6,000 light-years, irradiated the hemisphere facing it, depleted the ozone layer over that hemisphere for a period of months to years, and contributed to the die-off alongside the glaciation. We don't know this happened. The evidence is suggestive but not conclusive. There is no gamma-ray iridium layer the way the Cretaceous-Paleogene boundary has its iridium from the impact. Gamma-ray bursts don't leave elemental signatures the way asteroid impacts do. But the pattern is there. The geographic distribution of losses is there. The ozone depletion model matches the rate of loss. And the math of how many GRBs should have occurred within the lethal radius over 450 million years is not zero. We don't know. The rock is telling us something. We haven't finished reading it yet. A quasar is what you get when matter falls into a supermassive black hole fast enough to release more energy than 100 billion stars. The accretion disk, the flattened ring of material spiraling inward around the black hole, heats to temperatures high enough to emit across the entire electromagnetic spectrum, from radio waves to X-rays to gamma rays. The two poles of the system, perpendicular to the disk, produce jets of relativistic plasma that can extend for millions of light years. When astronomers see a quasar but can't resolve the two jets separately because both appear to be coming from the same direction, meaning the jet is pointed directly at the observer, the object gets a different name. There are several blazars visible in the night sky right now. Not bright enough to see with the naked eye, but present, persistent, catalogued. Markarian 421 in the constellation Ursa Major, roughly 434 million light-years away. Markarian 501, BL Lacertae, the object that gave the class its original informal name. You are receiving photons from these objects right now, the same objects whose jets, if you were directly in their path at close enough range, would be lethal. You are not directly in their path. You are just close enough to see a faint point of variable light. The distinction between a point of light in my sky and inside the kill zone is geometric. It depends entirely on angle and distance. At 400 million light-years, you are safely in the category of observer. At 4,000 light-years, the category changes. The Milky Way's own central black hole, Sagittarius A star, is currently quiet. But 4 to 8 million years ago, it wasn't. In 2010, two astronomers, Meng Su and Douglas Finkbeiner at Harvard, were processing data from NASA's Fermi Gamma Ray Space Telescope when they found something that should not have been there. The Milky Way emits a soft, diffuse gamma-ray glow across its disk. Cosmic rays interacting with gas and dust, a background hum from all the violent small-scale processes distributed across 100,000 light-years of galactic activity. This was expected. What was not expected was the two enormous lobes extending above and below the galactic plane, perpendicular to the disk, pointing away from the center in both directions. Each lobe extends roughly 25,000 light-years. Together, the pair, now called the Fermi bubbles, spans 50,000 light-years, nearly the full diameter of the galactic disk, just turned on its side. They are made of gamma-ray emitting material. High-energy particles and hot gas moving outward from the galactic center at hundreds of kilometers per second. The origin is not settled science, but the leading candidate is Sagittarius A star, the supermassive black hole at the center of our galaxy. Currently 4 million solar masses, currently quiet, at some point 4 to 8 million years ago, underwent a period of activity. Matter fell in faster than the system could radiate it quietly. A jet formed, or a burst of star formation around the center, created a massive outflow. Either way, something from the galactic center released an enormous amount of energy and drove material outward through the surrounding gas. We are 30,000 light-years from that center. The Fermi bubbles are still expanding. The outburst happens while early hominins were beginning to walk upright in Africa. The shock wave is still moving. The question this leaves open is, what happens when Sagittarius A star wakes up again? Here's what almost nobody considers about the galactic center. Astronomers refer to Sagittarius A star as currently quiescent. In the language of galactic nuclei, this means it is not actively accreting large amounts of matter. It occasionally flares, brief brightening events that last hours, probably caused by small objects or gas clouds falling in. But by the standards of active galactic nuclei, it is quiet. Ciphered galaxies, which are similar to the Milky Way in structure and mass, have active galactic nuclei roughly 100 to 1,000 times more luminous from their centers than ours currently is. We know what Sagittarius A star looks like when active because we can observe analog systems in nearby galaxies. But more specifically, astronomers found X-ray light echoes from SGRA star in the surrounding molecular clouds. Clouds of dense gas near the galactic center that are currently being illuminated by X-rays, not from any current source, but from a reflection. Photons bouncing off the clouds from a burst of activity that originated at SGRA star roughly 100 to 300 years ago. The SGRA star that existed in the late 1700s or early 1800s was briefly far more active than today. The flash already happened. The echoes are still traveling outward through the surrounding gas, and we are watching them in real time. Something happened at the center of our galaxy within recorded human history. The echo is there, and the Fermi bubbles represent something far larger from something far older, still expanding through the space above and below the disk we live in. SGR A star is not a threat we can quantify on human timescales. The distance is protective. The current activity level is protective. But currently quiescent is not structurally incapable of activity. It is a snapshot. And the snapshots in the recent past show variation. The Fermi bubbles are evidence of variation. There is a difference between a burst of light and a burst of particles. Electromagnetic radiation, gamma rays, X-rays, visible light, travels at the speed of light and interacts with matter primarily through absorption and ionization. A magnetar burst or gamma ray burst sends a wave of photons outward. These photons interact with Earth's atmosphere, ionizing atoms, producing secondary particles, potentially stripping ozone. Cosmic rays are different. They are actual particles, protons, helium nuclei, heavier atomic nuclei, accelerated to near light speed by violent astrophysical processes. Supernova, magnetars, gamma-ray burst afterglows, active galactic nuclei. These particles arrive from all directions continuously. The energy range of cosmic rays detected at Earth spans from energies similar to a thrown baseball up to energies so extreme that single particles carry the kinetic energy of a fastball, roughly 100 joules packed into a single proton. These ultra-high-energy cosmic rays, detected by the Pierre Auger Observatory in Argentina and the Telescope Array in Utah, arrive at rates of perhaps 1 per square kilometer per century at the highest energies. They pass through the atmosphere. They pass through you. Every second, roughly 1 cosmic ray passes through every square centimeter of your body. Most of them don't interact. The ones that do create tiny tracks of ionization in your cells, single-strand breaks in DNA that your repair mechanisms fix almost immediately. The background rate is folded into your biology. You have been inside this field your entire life. But the background rate is averaged across a galactic environment. Near a violent source, the flux increases. Near a magnetar, a GRB source, a blazar jet, the particle flux becomes something else. Something the repair mechanisms weren't calibrated for. The distinction between the universe you live in now and a universe with a nearby GRB is not a difference in kind. It is a difference in flux. More particles, more ionization, More DNA damage than your cells can repair. That's the entire mechanism. Start here. The air in your lungs. The nitrogen and oxygen atoms filling your alveoli right now, or at some point in the deep past, part of the interstellar medium, the diffuse gas between star systems. They were gathered by the sun's gravity, processed through stellar activity, incorporated into the geological cycling of Earth, and arrived in the atmosphere over billions of years. In the broadest sense, you are breathing the local interstellar medium, but you're not breathing it raw. You are breathing it inside a structure. The sun emits more than light. It emits a continuous stream of charged particles, the solar wind, which flows outward from the solar surface at speeds of roughly 400 kilometers per second. This solar wind doesn't stop at the outer planets. It continues past Neptune, past the Kuiper Belt, past the outermost edges of what we think of as the solar system. At roughly 100 to 120 times the Earth-Sun distance, the solar wind slows down abruptly. It hits the interstellar medium coming the other way. The region where the solar wind decelerates is called the termination shock. Beyond that, the region where solar wind still dominates but has slowed, the heliosheath. And the outer boundary, where solar wind particles are no longer the dominant component, the heliopause. This entire structure is called the heliosphere. Everything you have ever experienced, every human who has ever lived, every spacecraft we have launched, every rock sampled from the Moon and Mars, all of it has been inside the heliosphere. Voyager 1, launched in 1977, crossed the heliopause in August 2012. It took 35 years, traveling at roughly 17 kilometers per second, to exit the bubble we live in. Inside the heliosphere, the solar wind deflects a significant fraction of the galactic cosmic ray flux. Outside the heliopause, the cosmic ray flux approximately doubles. We have instruments there now. We know what it reads. On August 25, 2012, a spacecraft the size of a small car became the first human-made object to enter interstellar space. Voyager 1 didn't carry a flag for this moment. There was no announcement on board, no ceremony. The transition was identified later, on Earth, by 3 independent lines of evidence processed by scientists who had been waiting for the crossing for years. The magnetic field direction changed. The density of plasma surrounding the spacecraft changed. Most significantly, the count rate from the spacecraft's cosmic ray detectors, which had been rising for several months as Voyager approached the boundary, jumped sharply on that date and stabilized at a new, higher baseline. Outside the heliosphere, cosmic ray flux from galactic sources is roughly 2 to 3 times higher than inside. Voyager 1 registered this step function directly. The instruments weren't damaged. They logged the number. For 35 years, the spacecraft had been inside the bubble that we have always lived in. The bubble defined by the solar wind, built and maintained by the same process that sends light and warmth to Earth. And then the bubble ended, and the rest of the galaxy was there, measurably in the particle count. Don Gurnett at the University of Iowa, analyzing plasma wave data, confirmed the crossing definitively in 2013 using the sound of the medium, literal oscillations in the plasma density that translate to frequencies detectable as audio signals. The plasma outside the heliosphere was denser and at a different frequency than inside. The spacecraft rang like a tuning fork in a new room. For 35 years, it had been in the old room. But here's the first piece that opens into something larger. What Voyager 1 found was the end of our protection. And what surrounds the heliosphere, what Voyager is currently moving through, is not just empty interstellar space. It is something with a history. Zoom out from the heliosphere to the scale of our stellar neighborhood. Within roughly 1,000 light-years of the Sun, the interstellar medium is noticeably different from the galactic average. The density of gas and dust in this region is approximately 10 to 100 times lower than the typical density elsewhere in the Milky Way disk. The temperature of this gas is much higher, millions of degrees, compared to the tens of thousands typical of warm interstellar gas. This region is called the local bubble. Low-density, high-temperature gas is a signature. It means something energetic passed through and heated the material, blowing a cavity. The mechanism that creates this kind of structure is well understood: supernova. Over the past 10 to 15 million years, researchers have traced the origins of the local bubble to a series of approximately 14 to 20 supernovae, likely originating from the Scorpius-Centaurus-OB Association, a group of massive young stars whose remnant population still exists in the Scorpius and Centaurus star-forming region, roughly 400 to 500 light-years away. One by one, the most massive members of this association reached the end of their lives and exploded. Each explosion added energy to the cavity. The shock waves merged. The structure grew. We live inside it. The Sun entered the local bubble approximately 5 million years ago and has been inside it since. The bubble's boundary, where the hot, rarefied gas meets the denser surrounding medium, is not a stable wall. It is expanding. Slowly, but expanding. The solar system is inside a scar. The scar was made by events that would have been lethal to Earth if they had occurred within 20 to 30 light-years. They occurred further away. We are the beneficiaries of this geometry. We haven't moved far from where the supernova happened. We are still inside the remnant of their aftermath. Here's what we don't know about the supernova that created the local bubble. We know approximately how many there were. 14 to 20 is the current estimate. We know approximately when they occurred, over a period of 10 to 15 million years. We know approximately where the progenitors came from, the Scorpius-Centaurus Association. What we don't know is how close the nearest one was. Some modeling puts the closest event at 50 light-years or more. Some evidence suggests it may have been within 30 light-years. The kill radius for a supernova is generally cited at roughly 26 light-years for a direct high-energy event. Ozone depletion becomes significant at up to 100 light-years in some models, depending on the properties of the specific explosion. We can't reconstruct the distance of the closest event to better than an order of magnitude. The evidence in the geological record elevated concentrations of specific isotopes like iron-60 and manganese-53 in deep ocean sediments, produced only in supernovae and delivered to Earth by cosmic rays and fallout, tells us the events happened and approximately when. It doesn't tell us the precise distance. There are sediment layers that carry these isotopic signatures. The layers that mark roughly 2.6 million years ago, 6 million years ago, and others further back show elevated supernova byproducts. These are the footprints. The events themselves are gone. Whether any of them were inside the 26 light-year threshold is a question we cannot currently answer with confidence. That's consistent with several possible histories, including some that came closer than felt comfortable at the time. The Crab Nebula is visible through a small telescope from Earth, a faint, fuzzy patch in Taurus, about 6,500 light-years away. In 1054, Chinese and Arab astronomers recorded a new star that appeared in the daytime sky and remained visible for 23 days. The explosion itself was seen from Earth with the naked eye. In the center of what that explosion left behind, there is a pulsar, a neutron star rotating 30 times per second. Every revolution, its magnetic axis, misaligned from its rotation axis, sweeps two beams of radiation across the sky. One beam pointing forward, one pointing back. The beam consists of radio waves, X-rays, visible light. Every 33rd of a second, one of those beams sweeps across the direction of Earth. We receive it. Telescopes detect the pulse. 30 times per second, a lighthouse located in the Crab Nebula illuminates our instruments. But the Crab pulsar is relatively ordinary. It is young and energetic, but it is not a magnetar. The beam you receive at Earth from the Crab, after traveling 6,500 light-years, is a faint radio pulse, detectable only with instruments. Now consider the same geometry with a magnetar. A magnetar spinning, as some of them do, tens of times per second. The sweep of its magnetic poles across space carries not a radio pulse, but a gamma-ray beam with the energy density of the 2004 event. Every rotation, continuously. If such an object were close enough and aligned correctly, Earth would receive the beam on each rotation. Every second, or every 30th of a second, or whatever the rotation period happens to be, the beam would sweep across this planet. We haven't found one at that geometry. But the word haven't deserves to sit uneasily. The population of magnetars is incompletely catalogued. We know of a few dozen. The estimates for the actual number in the Milky Way run to thousands. We can only detect the ones that happen to be pointing at us. The mechanisms by which a black hole kills at a distance are more varied than the name suggests. For a stellar mass black hole, say 10 solar masses, the event horizon sits at roughly 60 kilometers from the center. That's the sphere inside which nothing can escape. But the black hole's influence extends far beyond that boundary. At roughly 3,000 kilometers from a 10 solar mass black hole, the tidal gradient, the difference in gravitational pull between the side of your body facing the black hole and the side facing away, becomes strong enough to begin stretching you. The technical term is spaghettification, and it is precisely what it sounds like. The gradient overcomes the structural cohesion of biological material before you reach the event horizon. For a stellar mass black hole, you die well outside the event horizon. But for a supermassive black hole, Sagittarius A star at 4 million solar masses, or the object at the center of Messier 87 at roughly 6.5 billion solar masses, the geometry changes. The event horizon of a supermassive black hole is so large that the tidal gradient at the event horizon itself is relatively mild. For Messier 87's black hole, the tidal force at the event horizon is gentle enough that a human body would not be immediately spaghettified upon crossing it. you could cross the event horizon of the Messier 87 black hole alive. The problem is that you would have crossed a threshold from which no information can escape, into a region that terminates in a singularity. You would be alive. You would be causally disconnected from the rest of the universe. The death would come later at the singularity, or from radiation processes inside the horizon. But by the time the danger was apparent from outside, you would already be inside. Death here begins before you feel it. Before any instrument inside or outside can confirm what has happened. The event horizon is invisible. The passage through it is physically unmarked. You cross it the way you cross a maritime border in the open ocean. Nothing changes at the moment of crossing, but everything about what the laws permit has already shifted. There is no surface to a black hole. This is not a poetic statement. It is a technical fact that the mind keeps sliding off of. When astronomers say the event horizon, they are describing a mathematical boundary, a surface where the escape velocity equals the speed of light. There is no physical object there, no wall, no membrane, no color change, no temperature gradient, no sound. The matter that originally formed the black hole, the core of a dead star, is compacted into the singularity at the center, a region where our current equations break down. The event horizon is the boundary around that singularity where the geometry of space-time closes off. It is not made of anything. You cannot see it with your eyes. You cannot detect it with your hands. You cannot touch it. You can only calculate where it should be based on the mass of the system and the equations of general relativity. And those calculations are good enough that we have confirmed them observationally. The Event Horizon Telescope collaboration produced the first image of a black hole's shadow in 2019. Messier 87 central black hole, 65 million light-years away. What the image shows is not the event horizon itself, but the shadow it casts on the light bending around it. The photon sphere, the innermost region where light orbits. The event horizon is inside that shadow. We are watching a region defined entirely by calculation. The discomfort here is not about falling in. It is about the principle it demonstrates. The most fundamental kill threshold in the universe leaves no physical mark. The danger is fully encoded in the mathematics of the surrounding space. The boundary is real, precise, and has consequences. And it is, to any available sense, invisible. This is the same principle as every other kill mechanism in this journey. The magnetar's field extends through empty space without visible announcement. The GRB beam is invisible until it's already passing through you. The cosmic ray travels without flagging its origin. The universe doesn't post warning signs. For a non-rotating black hole, the event horizon is a sphere. Clean geometry. The interior is inaccessible. The exterior is ordinary space-time, curved significantly near the horizon, but otherwise navigable. A rotating black hole is different. The mathematics that describes it, the Kerr solution published in 1963, produces a second surface outside the event horizon, not a physical surface, a region of space-time. It is called the ergosphere. In the ergosphere, the rotation of the black hole drags space-time itself. Frame dragging, the warping of space in the direction of the black hole's spin, is present outside the ergosphere too, but outside it, You can compensate. You can apply thrust and move in the direction opposite the rotation. You can counteract the drag. Inside the ergosphere, you cannot. The space-time itself is rotating faster than light in the coordinate sense. Not faster than light locally. Locally, everything is still below light speed. But in terms of the global reference frame, the rotation rate exceeds the limit. To remain stationary in the ergosphere with respect to a distant observer, you would need to exceed the speed of light. Since you cannot do that, you are dragged along. You can still escape the ergosphere. It extends beyond the event horizon, and there is still a path out. But while inside it, you are co-rotating with the black hole. You cannot point your thrust in any direction that stops the rotation. Roger Penrose identified in 1971 that objects in the ergosphere can theoretically extract energy from the black hole's rotation, the Penrose process, by splitting into two pieces, one of which falls toward the horizon, carrying negative energy, and the other escaping with more energy than the original particle had. This is not science fiction. It is a well-established result of the Kerr metric. The ergosphere is a region where the geometry of space-time has become active, where the structure of space enforces motion, where stationary is not available as a choice. It is one of several places in the universe where the concepts you use to navigate your life, distance, direction, stillness, control, are simply not applicable. The star that will gently illuminate your morning was 4.5 billion years ago, a T Tauri star. A T Tauri star is a young sun, still contracting toward the main sequence, still accumulating material from the surrounding disk, still settling into the nuclear fusion process that will define its stable life. The current sun's X-ray luminosity is modest. By the standards of active stars, it is well behaved. A T Tauri phase star of the same mass emits 1,000 to 10,000 times more ultraviolet and X-ray radiation than the current sun, not as a brief flare, continuously for tens of millions of years. Earth existed during this phase. The planet was already formed, the accretion had happened, the moon-forming impact had happened, the solid surface was already present. But the early sun was bathing this world in radiation levels we would today describe as sterilizing. Life did not begin on land during this period. Life didn't begin at the surface. The first reliable evidence for life on Earth, microbial fossils and chemical signatures, dates to roughly 3.5 to 3.8 billion years ago, by which point the sun had aged past its most violent phase and the atmosphere had developed to partial protection. Before that window, the surface was effectively open to the sky. The evidence for where early life retreated is in the deep-sea hydrothermal vent ecosystems that persist today, places where sunlight has never reached, where the energy comes from chemical gradients rather than radiation. The deepest branches of the tree of life cluster around high-temperature chemosynthetic organisms that don't use sunlight at all. This is not coincidence. This is the record of what was safe and what wasn't. The star that will rise over your horizon tomorrow was the most dangerous thing in the early solar system. The danger came from the closest source. Life found the only shelter available, underground, in the dark, at the bottom of the ocean. The T Tauri phase typically lasts from 1 million to 100 million years, depending on the star's mass. During this period, a star of solar mass emits ultraviolet flux, strong enough to photoevaporate the atmospheres of planets in the inner system. There is evidence in our own solar system that this happened. The inner planets, Mercury, Venus, Earth, Mars, have atmospheric compositions consistent with secondary atmospheres rebuilt from volcanic outgassing and comet impacts after their primary atmospheres were partly blown away by the early solar wind and radiation. In other star systems, the T-Tauri phase may be more extreme, more prolonged, or both. For systems around stars slightly more massive than the Sun, F-type stars, the T-Tauri phase is shorter, but the radiation is more intense. For stars less massive, K and M dwarfs, the T-Tauri phase is often longer, and the habitable zone sits closer to the star, meaning the radiation environment during those millions of years is significantly worse for any planet where liquid water might be stable. M-dwarf systems, the most common type of star in the galaxy, are now understood to have early radiation environments so aggressive that the habitability of their inner planets is genuinely uncertain. Proxima Centauri, the nearest star to the Sun, is an M-dwarf that still produces large flares routinely. Proxima Centauri b, the planet in its habitable zone, receives on a typical flare day more ionizing radiation than Earth receives during its worst solar events, not during the T-Tauri phase. Now, routinely, the flaring never stopped. The concept of a habitable zone was defined by temperature, the region around a star where liquid water could be stable. But temperature is only one variable. Radiation is the other. And for much of the galaxy's history, around most of its stars, the zone where temperature was right was also a zone where the radiation was not. The Milky Way is not uniformly dangerous. At the center, approximately 26,000 light-years from Earth, Sagittarius A star sits surrounded by the most densely populated region of the galaxy. Stars crowd together. Massive stars form and die faster. Supernovae occur more frequently. The galactic center has the highest concentration of every violent astrophysical process we know of. At the edge, where the density of stars falls off and the disk thins, the problem is different. The metallicity of the outer galaxy is lower. Planets form with less material. The heavy elements necessary for complex chemistry are less abundant because there have been fewer generations of stars to produce them. Somewhere between too violent at the center and too sparse at the edge, there is a ring of the galactic disk where conditions have been consistently moderate. High enough metallicity for rocky planets with complex chemistry. Far enough from the violent center that the radiation environment is survivable on long time scales. This region is called the galactic habitable zone. Its boundaries are roughly defined between approximately 20,000 and 35,000 light-years from the galactic center, within a few thousand light-years of the galactic midplane. The Sun sits at approximately 26,000 light-years from the center, inside the galactic habitable zone. Not just inside it, near the inner edge of the safest part. Additionally, the solar system is currently located between two of the Milky Way's spiral arms, near the inner edge of the Orion spur, between the Sagittarius arm and the Perseus arm. Spiral arms are regions of higher density, more active star formation, more massive stars, more supernova. Between the arms, the environment is quieter. This combination, the right mass star, the right orbital distance from the star, the right position in the galaxy, is statistically unusual, not unique, but not generic either. 370 million years ago, approximately 75% of all species on Earth were eliminated. Over a period of roughly 20 million years, not a single event, but a prolonged crisis, the Devonian fauna collapsed. Fish, coral reefs, and early plants on land were all devastated. The cause has been debated for decades. Multiple pulses of extinction suggest multiple causes or prolonged destabilization rather than a single event. Volcanism and glaciation are the leading candidates. But there is a recurring thread in the Devonian extinction literature. The sea level records and the distribution of survivors suggest significant UVB radiation reaching the surface. Spore damage in fossil plants from this period, abnormal, malformed spores consistent with UVB exposure, has been documented in multiple locations. The Kellwasser events, the primary pulses of Devonian extinction, coincide with evidence in the plant record that something was wrong with the sky. The cosmic interpretation, a nearby gamma ray burst or similar event, stripping ozone over one or both hemispheres, compounding the effects of whatever climatic stress was already ongoing. The combination would be consistent with the data. The Devonian extinction does not have a clean cause. It may have had many causes, but the UV signature in the plants is real, and the UV scenario fits the geography of the survivors in ways that strictly climatic explanations don't fully account for. We have two extinction events, Ordovician and Devonian, with UV signatures. Neither has been definitively attributed to a cosmic source. The evidence is circumstantial, pattern matching rather than direct. But the pattern is there. Twice. September 1st, 1859. British astronomer Richard Carrington was sketching a group of sunspots when he noticed a sudden, brilliant white flash erupt from the solar surface. He watched it for about 5 minutes. He had seen something nobody had documented before, a solar flare observed in white light, visible to the naked eye without a filter. 17 hours later, the effects arrived at Earth. Telegraph operators across North America and Europe reported sparks leaping from their equipment. Some received shocks through their instruments. Some found that they could continue sending and receiving messages even after disconnecting their systems from their power supplies. The geomagnetically induced currents were strong enough to drive the system independently. The aurora was visible from the tropics, Cuba, Colombia. The Carrington event is the largest solar storm in recorded observational history. If it occurred today, assessments by NASA and the National Academy of Sciences estimate it would knock out significant portions of satellite infrastructure, disrupt GPS, potentially cause widespread transformer failures in power grids at high latitudes. Recovery timelines measured in months to years. A financial impact estimated in the trillions of dollars. This was an ordinary flare from a stable main sequence star at its median activity level on a middle-of-the-road day in the Sun's 11-year cycle. The flare that could do this is 10,000 times less energetic than the events from magnetars we've already described. It arrives at Earth, not at 1,000 or 6,000 light years, but at the distance of 8 light minutes. The Sun is close. Very close. And the Sun, at its most violent recorded event, produced something that would severely damage modern technological civilization. Scale that up by 4 or 5 orders of magnitude and move the source anywhere in the galactic neighborhood, and the word Carrington becomes a memory of the gentlest version. In 1964, a rocket experiment carrying X-ray detectors was launched into suborbital space and detected for the first time bright X-ray sources outside the solar system. One of them was Cygnus X1, a point in the constellation Cygnus. Brown-based follow-up identified it as a binary star system, two objects in orbit around each other. One was a supergiant star. The other was compact and massive and invisible in optical wavelengths. The compact companion was later confirmed as a black hole of roughly 21 solar masses, the first stellar mass black hole directly confirmed. The mechanism, the supergiant star, much larger than its companion, sheds material in a stellar wind captured by the black hole's gravity. The captured material forms an accretion disk, a flat, swirling ring of gas heating to tens of millions of degrees as gravitational energy converts to heat. The disk radiates in X-rays. The X-ray luminosity of Cygnus X1 is roughly 10 million times the total luminosity of the Sun. At its distance from Earth, roughly 7,000 light-years, we receive only a faint X-ray signal, detectable only with space-based instruments above the atmosphere. But there are several thousand known X-ray binaries in the Milky Way. The distribution is roughly uniform across the disk. At any given moment, some of them are emitting steady X-ray radiation. Some undergo outbursts, transitions from quiescent to active states associated with changes in the accretion rate that can increase their X-ray luminosity by factors of 10 to 100 in days or weeks. We can model what the X-ray flux from an X-ray binary outburst would be at various distances, and 100 light-years, potentially significant. At 50, severely damaging. At 20, survivable scenarios narrow to near nothing. The distribution of X-ray binaries in the galaxy is not designed around safe clearance distances from Earth. In 2007, a graduate student named David Narkovic was working through archival data from the Parkes Radio Telescope in Australia when he found something that shouldn't have been there: a burst of radio waves, lasting about 5 milliseconds, bright enough to stand out clearly from the noise. The dispersion measure, the way the signal smears across frequencies as it passes through ionized plasma, indicated the burst had traveled an enormous distance, billions of light-years possibly. The signal had arrived from outside the Milky Way. Nobody had seen one before. It was named a fast radio burst. Now we know of thousands. Most are extragalactic. The dispersion measures place them at distances of hundreds of millions to billions of light-years. Some of them repeat. Some are apparently one-time events. Their sources for most detections are unknown. In 2020, a magnetar inside our own galaxy, SGR 1935 plus 2154, located roughly 30,000 light-years away in the constellation Vulpecula, produced a burst simultaneously detected by radio telescopes on Earth as an FRB-like event and detected by gamma-ray observatories. For the first time, we had a known source for a fast radio burst. It was a magnetar, a starquake. The same mechanism as the 2004 event. This doesn't mean all FRBs are magnetars. The energetics are strained by that hypothesis for the most powerful events, and the population may be heterogeneous. but it establishes that one class of FRBs, at minimum, is produced by the same objects that produced the event that measurably affected Earth's ionosphere from 50,000 light-years away. The FRBs we detect from billions of light-years away are detectable because the universe is transparent to radio waves at those frequencies. The same burst from much closer would arrive with much higher power. We don't know the rate of nearby FRB events. We know the rate of detectable ones. Those are not the same number. Enrico Fermi reportedly asked at a lunch in 1950, "Where is everybody?" The universe is 13.8 billion years old. The Milky Way contains hundreds of billions of stars. A significant fraction of them have planets. The chemistry that produces life appears to operate on timescales of hundreds of millions of years. There has been enough time, in principle, for intelligent life to arise and spread to every corner of this galaxy many times over. And yet, silence. No signals. No artifacts. No evidence. The Fermi paradox has accumulated dozens of proposed resolutions. The Great Filter hypothesis suggests that somewhere in the chain, from simple chemistry to star-faring civilization, there is a nearly impassable barrier. The Rare's hypothesis suggests that Earth's conditions are far more unusual than optimistic estimates suggest. Others suggest life is common, but intelligence is rare, or that intelligence is common, but civilization is fragile. One resolution doesn't get discussed as often as it deserves. Perhaps the universe is not quiet because life is absent. Perhaps it is quiet because the kill radii are large enough that complex technological civilizations regularly get sterilized before their signals would be detectable to us. Not every star, not every system, but enough of them. A magnetar burst from within 30 light-years resets the surface of a planet. A GRB within 6,500 light-years in the beam direction resets it more thoroughly. An active galactic nucleus period sends enough high-energy radiation across intergalactic distances to be measurable at Earth. The universe has mechanisms to hit reset, and they operate on timescales that feel geological from a human perspective, but are quick by the standards of cosmic evolution. We may be in a window of galactic quietude that opened a few billion years ago and will eventually close, as windows do. The silence might not be the absence of life. It might be the record of what the universe has already done to it, repeatedly, across 400 billion stars. The Andromeda Galaxy, Messier 31, our nearest large spiral neighbor, is approaching. Currently 2.5 million light-years away, Andromeda is moving toward the Milky Way at approximately 110 kilometers per second. The two galaxies are on a collision course that will play out over the next 4 to 5 billion years. Galaxy collisions are not collisions in the conventional sense. The distances between stars are so vast that the probability of any two stars actually striking each other during the merger is negligible. What merges are the gravitational potentials, the shapes of the galaxies, their dark matter halos, their gas reservoirs. The two galactic disks will pass through each other, disturbing stellar orbits, triggering massive waves of star formation as gas clouds compress and fragment. Star formation means new massive stars. Massive stars mean new supernova, new neutron stars, new magnetars, new potential GRB progenitors. The star formation rate during the merger could increase by factors of 10 or more. For the solar system, whichever direction it ends up orbiting after the gravitational disturbance rearranges the galactic structure. The local environment of stars will change. Stars currently far from the Sun may be thrown into closer orbits. The stellar density in the post-merger galaxy will be different in ways that current models can sketch but not predict in detail. The merger also potentially activates the supermassive black holes. Both Andromeda and the Milky Way have central black holes. When the galaxies merge, the two black holes will begin to spiral toward each other. The gas disturbed by the merger may funnel material toward both nuclei, potentially triggering active galactic nucleus phases in both. The Sun will be approaching the end of its main sequence life at that point. Whatever is alive here, if anything, will be living in a fundamentally different galaxy. The sky will no longer be quiet. The galactic habitable zone isn't just a concept. Astronomers have attempted to map it. The current best estimates suggest the galactic habitable zone encompasses roughly 10% of the stars in the Milky Way. The other 90% exist in regions where the combination of low metallicity, high radiation, or proximity to violent events makes sustained complex life unlikely over billion-year timescales. Globular clusters, ancient, dense collections of hundreds of thousands to millions of stars, might seem like promising locations. They are old enough for complex chemistry to have developed, but they are too dense, and their density was worse earlier. In the early globular cluster era, the stellar density was so high that GRBs and supernova from nearby stars would have exposed all cluster members to repeated radiation events. The dynamical interactions between stars, close approaches, exchanges in binary systems would have disrupted planetary orbits repeatedly. The metallicity in many globular clusters is too low for rocky planets. The galactic center is too violent. The galactic outer disk is too metal poor. The galactic bulge is overcrowded with stars of varying ages and radiation histories. And even within the galactic habitable zone, the quietude is not uniform or permanent. Different parts of the zone are at different distances from the current positions of massive star associations. Different neighborhoods have different supernova histories. The quiet we experience is a local measurement, not a property of the zone as a whole. The Earth does not sit in the quietest place in the Milky Way. It sits in a quiet enough place for long enough at the right time. That's a different thing. Mars took approximately 500 million years to die. Not suddenly, not from an impact, not from a single catastrophic event. Mars had a magnetic field, a global dynamo similar in structure to Earth's, generated by convection in its molten iron core. The field protected the early Martian atmosphere from the solar wind, the same way Earth's field protects ours today. The Martian core cooled. The cooling was inevitable. Mars is smaller than Earth, and smaller bodies lose heat faster than larger ones. The surface area to volume ratio works against you. As the core solidified from the outside inward, the convective motion that generates a planetary magnetic dynamo slowed and eventually stopped. The magnetic field faded. Over perhaps 50 to 100 million years, the global dipole weakened and fragmented into localized crustal magnetic fields. Remnants of the ancient field frozen into the rock when the dynamo was still operating. These remnants are measurable from orbit today. Without the field, the solar wind reached the upper atmosphere directly. Charged particles from the sun arriving continuously, stripped ionized gas from the top of the Martian atmosphere. The process is slow but relentless. Billions of particles per second across billions of years, adding up to the loss of most of a planetary atmosphere. Today, Mars has an atmospheric pressure roughly 1% of Earth's. The ultraviolet radiation reaching the Martian surface is intense enough to sterilize exposed rock on timescales of hours. The water that once flowed there, the ancient riverbeds, the lake beds, the polar ice, is either frozen or escaped to space. The death of Mars was not dramatic. It was the sun, slowly, persistently, reaching across the distance of 150 million to 230 million kilometers, eroding the thin atmospheric shell until the surface became incompatible with liquid water and complex chemistry. Death took 500 million years. It was patient. The distance didn't matter. The Fermi bubbles extend roughly 25,000 light-years above and below the galactic center. Their inner edge, at the galactic center, is approximately 26,000 light-years from Earth. The upper boundary of the northern bubble extends into the volume of the galaxy we inhabit, not at Earth, but in our general direction. The bubbles are not static. The hot gas inside them is moving outward at roughly 900 to 1200 kilometers per second. The shock wave at the leading edge, where the expanding hot gas meets the surrounding cooler interstellar medium, is propagating outward as we speak. Whether the expanding Fermi bubble shock will ever directly interact with the Sun's local neighborhood depends on geometry and the detailed structure of the surrounding interstellar medium. At current velocities, it would take tens of millions of years for any part of the bubble structure to traverse the distance to the solar system, assuming it continues expanding in our direction. Tens of millions of years is not never. It is just not now. The 2019 discovery of X-ray chimneys by the XMM Newton Observatory, narrow channels of hot gas connecting SGRA star to the Fermi bubbles, suggesting active transport of material from the galactic center through the disk, confirmed that the galactic center and the bubbles are still thermally connected. The system is not entirely dormant. What we don't know is the schedule. The Fermi bubbles were discovered in 2010. Their full three-dimensional structure is still being mapped. Their age is constrained, but not precisely known. The conditions that would trigger a new outburst from SGRA star, a significant enough infall of material to restart energetic activity, are being studied but not predicted. The bubbles are out there, growing, moving. We don't know exactly where their expansion goes from here. The ocean floor records things that nothing else does. Sediments accumulate at the bottom of the ocean at rates of roughly 1 to 10 centimeters per 1,000 years, depending on location and conditions. Material falling through the water column, including cosmic ray-produced isotopes and dust carried in from the interstellar medium, gets incorporated into these sediments and preserved. With careful drilling and analysis, oceanographers and cosmochemists can read this record backward in time. Two isotopes are particularly useful: iron-60 and manganese-53. Iron-60 is not produced in significant quantities by any process other than supernova nucleosynthesis. It has a half-life of about 2.6 million years, long enough to travel across interstellar distances and be incorporated into sediments, short enough that it doesn't persist indefinitely. Its presence in sediment layers is a direct indicator of recent supernova material delivery. Multiple research groups have found iron-60 enrichments in deep-sea sediments at depths corresponding to approximately 2.6 million years ago, 6 million years ago, and other periods. The 2.6 million year event corresponds roughly to the Pliocene-Pleistocene boundary, a period of significant climate change and the spread of grasslands in Africa. The same period when the ancestors of modern humans were beginning to diverge from other hominins. Whether the supernova that deposited that iron-60 layer had any direct biological effect is not established. The isotopic signature is there. The extinction record at 2.6 million years ago shows some marine fauna turnover, but nothing like the major extinctions. But the record is also not complete. We have sampled a small fraction of the ocean floor. The isotopic anomalies we found are real and are from real supernovae. The distances were survivable. We're still reading the sediments. There is something worth pausing on before the end. We have described a universe full of structures whose kill radii encompass solar systems, galactic arms, swaths of the disk. We have described events that have likely touched Earth before. We have calculated distances that are uncomfortable. And we are still here. You are still here. In a bed, in a room, on a planet that has been sitting inside the local bubble, the remnant of at least 14 supernovae for 5 million years, orbiting a star that is currently in a relatively quiet phase, in a galaxy whose central black hole is unusually inactive by the standards of its peers. The instruments we've built to look out at the universe are sensitive enough now to detect gamma-ray bursts at billions of light years. The Fermi telescope sees them routinely, several per month. The data shows us what the universe is capable of. The data also shows us that in our immediate galactic neighborhood, in our geological present, a level of ambient violence is at a low. This is not comforting in the simple sense. It is not a guarantee. The galactic center can flare. A nearby star can explode. A magnetar can undergo a starquake. None of these events announce themselves in advance. But what the data shows is that the complex life that took 4 billion years to produce on this planet, the multicellular organisms, the vertebrates, the primates, the everything leading to this moment, did so during a window of relative quiet in a location of relative calm. That quiet is a fact. The reasons for it are computable. The geometry that placed Earth outside the Fermi bubble path, outside the GRB lethal zone for most of its history, inside the galactic habitable zone, all of that is measurable. The quiet is not permanent. The protection is not designed. But the window has been long enough. For you. You started this knowing something. Not as a fact you could state, but as something lodged in the body. Distance is protection. The night sky is quiet. The stars are far away. Space is empty. The universe around us is, for now, not threatening. All of that is still true in one sense. The sun is between minimum and maximum activity in a normal cycle. The nearest magnetar is roughly 1,000 light-years away. The nearest known GRB progenitor capable of directing a beam at Earth is WR-104 at 8,000 light-years, and it hasn't exploded yet. The galactic center is inactive by galactic center standards. The Fermi bubbles are expanding, but won't reach our neighborhood for tens of millions of years. The local bubble, the ancient supernova remnant we inhabit, is still holding. In human terms, in generational terms, in civilizational terms, the sky is safe. What we've traced together is what safe is built on. The geometry that kept Earth outside the lethal radius of 14 or more supernova over 10 million years. The quietude of a galactic center that has demonstrably erupted in the past and carries evidence of more recent activity. The position between spiral arms. The stable middle-aged sun. The magnetic field that prevents the slow atmospheric loss that ended Mars. Safety here is not the absence of mechanisms that kill. It is the current configuration of distances and angles and activity levels. A configuration that has held long enough for complex life to arise, diversify, go through 5 major extinctions, rebuild, and arrive at this moment. The night is quiet because the current distances are what they are. Not because the mechanisms don't exist. They exist. They have coordinates. We have named them. And somewhere in another solar system, in another galaxy, right now, there is a world that is not in this configuration, that is inside the cone. That is within the kill radius. That is receiving at this moment the signal that travels faster than the warning. We know what that looks like from a distance. Here, the distance is still enough. We started with something you already knew. Distance is the oldest form of safety. We've traveled through a universe where that idea holds, but conditionally. Where death is encoded in geometry, in angles and distances, and magnetic field gradients extending through empty space. Where the most lethal events don't announce themselves. Where the border between observer and inside the kill zone is sometimes a mathematical surface with no physical marker, crossed without sensation, irreversible. And yet, the same universe that contains magnetars and gamma-ray bursts and blazar jets and expanding supernova remnants also contains a galactic habitable zone. A local bubble with survivable geometry. A sun that is right now at the quieter end of its range. A planet with a magnetic dynamo that has been running for most of its history, holding the atmosphere in place against the persistent reach of the solar wind. You are in a bed. On a planet that has been here for 4.5 billion years, that has survived the violent youth of its star. At least one probable cosmic ray sterilization event in the deep past. The slow death of Mars next door as a reminder of what happens when the field fails. 14 or more supernovae whose remnants we still inhabit. The universe's silence above you tonight is not absence. It is the current reading of a complex system of distances and angles that happens for now to add up to quiet. That is not nothing. That is almost everything. If your eyes feel heavy, let them close. If this felt like home, leave a comment when you wake up. If you're still here, the next chapter is waiting. The universe will still be here when you wake up. So will we.